buttery smooth. Okay. It's full time, right? Great. This is Adam Bry from Skyio, and he's going to talk to you about drones today, I would assume. Hopefully.
Yeah.
Here we go.
Cool. Yeah, so thank you all for coming. It's exciting for me to be here. I actually know very little about Berkeley, so I was a grad student at MIT, but of the major robotics programs, this is probably the one that I know the least about and have spent the least time at. So excited to be here and talk with you guys today. So my plan is actually to mostly talk about the research background that I did at MIT that kind of led into Skyio. So we didn't know it at the time, but a lot of the ideas that my co-founders and I were working on and playing with at MIT ended up becoming the company. Since you guys are mostly grad students now, I assume I thought that might be an interesting place to start. But really, I'm more than happy, mostly my hope is just to say interesting things that kick off questions. And I'd be more than happy to be interrupted at any time and answer anything that's on your guys' minds. So drones are super exciting. They're starting to show up everywhere. There's all kinds of really cool applications. People are starting to use them for interesting things. And you've probably noticed that Silicon Valley in particular has gotten super excited about the different market opportunities that are out there. So I'd like to start. We've cherry-picked some of our favorites of people flying drones today. Thanks to YouTube, we're starting to get a lot of videos that look like this, and this. This was a famous one. This was in New York. This guy actually got arrested. Yeah. I think it's cool that he loves it so much that he decides to go in after it. Yeah, so we, of course, have to end with the fish. So I think drones, more than any other technology right now, have just an enormous gap between sort of people what imagine and what you think you can do with them and what's possible with existing products. And I think it's worth kind of reflecting on, how did we get here? And so the idea of a drone, what we call a drone today, is actually not a new thing. They've been around for a really long time. They've probably been around for 30 or 40 years. They were just called RC helicopters. And there's been a series of kind of technological innovations that have gotten us to the point where what we call a drone is possible. So to begin with, 30 years ago, they were gas-powered devices that were basically RC toys. And in order to fly one of these things, you had to be pretty passionate and enthusiastic about tweaking little gas motors and building and maintaining and fixing them. Does anybody have experience with? No? Not a single RC hobbyist in the room? I'm shocked. Well, I am. So the next big step up from that was basically making them electric. And the breakthrough that made that possible was mainly lithium polymer batteries, and this happened about 15 years ago. And so that was a dramatic reduction in size, weight, costs, but they were still very difficult to fly. So it opened up the market a little bit, and more people started to use them, but the barrier to entry to be able to actually pilot them successfully was still pretty high. And the piece that came after that was starting to pull in a lot of the EE components that are coming out of cell phones. So in particular, the sensors, so MEMS, IMU, and GPS, made it possible to do basic stability augmentation and control on board, which made normal helicopters easier to fly, but it also opened up the possibility of doing things with multi-rotors, where, if you just map somebody's control inputs to the RPM of the 4 motors on a quadcopter, it's impossible to control. But if you filter that through a control system that's doing some kind of attitude stabilization using MEMS sensors, it becomes possible. And so by switching from a conventional helicopter to a multi-rotor, it's a major step down in mechanical complexity. And so it's a much easier thing to sort of build and maintain. And then the big one on top of that was just adding a camera to it, basically. And it turns out that a multi-rotor with a camera is a pretty fantastic thing that lots of people can use for lots of different things. but the key here is that nobody has actually, like the heritage of this device, so this is a DJI Phantom, is still basically an RC helicopter with a camera on it. And it was developed in a hobby market, not like a multi-billion-dollar consumer electronics market. And there's still, especially on the software side, just an enormous gap between what existing products have and what's possible with the right technologies, which is obviously one of the things that we're really excited about at Skydio. So a little bit of my background. So I know a lot about this because I grew up doing it. So it's always embarrassing for me to show these. Based on the hat, you'd think the picture was taken in like 1950, but it wasn't. I was just like a really cool 9-year-old. So this was, I think these are actually pictures from different competition aircraft I had. So this is really like building and flying these things as a kid is what got me interested in engineering. And I grew up like tinkering with them and building and modifying and trying to optimize them to fly better, and also pushing myself to become a better pilot. So when I was in high school, I was competing in radio control aerobatics, where you basically get given a set sequence of maneuvers, and then you get judged on how precisely you can do everything. So you probably surprised no one that I wasn't in like the most active social circles with a hobby like that. But at a certain point, I sort of switched from trying to be a good pilot myself to trying to make computers that could fly them better than the best human possibly could. So that led me to be a grad student in CSAIL at MIT. So I joined Nick Roy's group, the Advanced Robotics Lab. And when I got there, this was kind of the platform of choice. So people familiar with this? This is an Ascending Technologies Pelican. So the main sensor that we're using here is a laser range scanner, but it's also carrying a stereo camera pair, an Intel Atom processor, and this was kind of the main workhorse in the lab for a long period of time. So the LIDAR, I assume most people are familiar with LIDAR. It basically gives you like a planar slice of the environment at 40 hertz, 270-degree field of view, and it's a great sensor. It's just kind of heavy and expensive. So the first kind of algorithmic challenge to make this stuff work is very simple, just stability and control, like knowing where you are and how you're moving. And the key thing that enabled us to fly with these was a really high rate efficient scan matcher. So the idea with scan matching is pretty simple. You're basically taking successive scans from the sensor, which give you the red and green points there, and then trying to line them up, which is essentially an optimization problem. And so it's, like a lot of inference problems, it's kind of like nonlinear, and there's a lot of local minima. And based on the specifics of the problem, there are various things we did to get around that. This was actually work mostly done by my co-founder, Abe. But we ended up with a very efficient system that was kind of the base level building block for a lot of autonomous flight. And once we had that in place, you could start to pull in a lot of things that people were already doing on ground robots. So this is autonomously exploring the ground floor of this data center, the building at MIT, and running a 2D SLAM algorithm to build the map online. We probably have a couple of other environments in here. This is down in the basement. You'll note we have the foam boards taped to the wall there. Has anyone played with like LIDAR in a hallway? Yeah, so it doesn't work, right? Yeah. That's why we have the foam boards. I suspect we're just going to get more of the same here. So the furthest that we took this was building fairly large-scale maps going in and out of buildings. So this is a pretty good swath of MIT's campus. So I don't know if anyone's familiar with the campus. So this is this data center where we started. We flew out down the corridor, through a couple of hallways, around the outside, all on a single battery, all fully autonomous, and built up this kind of nice 3D point cloud of everything that we saw. But this is kind of as far as you could take this line of research, and there's some kind of obvious limitations in play in approaching things this way. So the big one is that we're assuming a 2.5D environment, where we basically assume that the whatever 3D structure is out there is just an extrusion of a 2D plan. And then we're also assuming unaccelerated flight of the vehicle. So it's essentially a holonomic system that you can just command motion at any time in any direction, and if you need to, you can stop and hover for as long as you want, which made all this stuff tractable, greatly simplified the problem, but also wasn't as interesting as things as these are really capable of. So as a result of this, both of these assumptions come into play. It basically means that you can't leave the hover regime. Like, you need to stay close to level, you need to move slowly. So one of my interests when I showed up was, what can we do to get away from this kind of paradigm? And to really force the issue, we thought it would be interesting to try to do this with a fixed-wing vehicle. And so the kind of high-level mandate was, can we do aggressive autonomous flight in and around obstacles using onboard sensors? So to get started, we sort of started trying to break things down from an algorithmic perspective, like what's going on here, what are the challenges? And I think that this is, I'll talk more about this later, but I think this is kind of typical of a research approach that people take. Like, what are the theoretical challenges in play to enable this kind of system to work? So the first is that we have uncertain dynamics. Like, especially with a fixed-wing vehicle, there's just no way that you can build a good enough model to really predict how the thing is going to move. And even if you did, it's subject to wind and other disturbances. So what that means is that purely open loop, your prediction of what the accuracy in your prediction of what the vehicle is going to do for a given control input just grows unbounded over time. And then on the other side, we also have noisy, spatially varying measurements. So your ability to estimate the state of the vehicle when you're using onboard sensors is fairly state dependent, or at least so we thought. Meaning that, like, if you're banked hard over and the LIDAR is just seeing the floor and the ceiling, that gives you very different information than if it's seeing, like, the nice sort of 2D plan that you're trying to localize against. So this, from a perception standpoint, I'm guessing you guys are familiar with, but this sets up kind of like a typical estimation problem where you have noisy dynamics, you have noisy measurements, and you're trying to fuse the two into a consistent state estimate. So we were kind of interested in thinking, what does this mean from a planning perspective? So are people familiar with POMDP, partially observable Markov decision process? So it's kind of like the full shebang in terms of difficult planning problems, like uncertain dynamics, uncertain measurements, and non-trivial dynamics, and trying to plan in a space where you can reason about all these things. So to model that, we came up with this kind of toy problem, where we said that you start, so you have some goal region you want to get to, which we have as the orange box here, and you have some initial estimate of where you are, represented by the blue circle, so we might be anywhere in that blue circle, and we want to try to basically get from wherever we are to the goal region. The challenge is that if we try to go directly there, there's a pretty good chance that we'll run into an obstacle because we don't know exactly where we are. And so there's this notion of a chance-constrained solution, which means we want to reach the goal while bounding the probability of collision, that you can formalize in a nice way where you sort of say that at any given time step the probability of collision is less than some threshold, and we want to make sure that we start at our estimate and end at the goal. So a valid chance-constrained solution might do something like this, where we start off and then go down to this kind of green region where we can get a good state estimate. So this is just like a 2D proxy for what we imagine the full high-dimensional problem to look like. Then we can collect some good information, lock in on exactly where we are, and then safely get up to the goal region. Of course, we'd like to be able to do that in some kind of optimal fashion, which might look something like this, where we go directly down, get what we need, head back up, and get to the goal. So one of the more typical motion planning approaches out there is called a rapidly exploring random tree. People familiar with this? Cool. So this is a sneak preview maybe. So the basic idea with an RRT is that you essentially rely on sampling and randomness to get coverage of the space that you're trying to explore. So the very simple idea of the algorithm is you just sample a new state from the state space and then somehow connect it to the closest space in Euclidean or some other sense, the closest other sample. And so you get this tree that kind of provably quickly explores the space. And it has this notion of probabilistic completeness, which means that as you run the algorithm towards infinite iterations, the probability that you have a solution converges to one. So our work kind of built on top of this, but extended it to information space. So the kind of key trickiness with that, which is what that toy problem gets at, is that the state estimate that you have, which is really part of your state, it's part of the memory of the system, is dependent on the path that you take to get there. And so you can kind of illustrate that here. Like if you follow path A and go straight, then you end up with this higher uncertainty, whereas if you go through the green region, you end up with this lower uncertainty. And so purely planning in the normal kind of physical state space of the problem doesn't allow you to solve it. You have to reason in this higher dimensional space, which is called information space. This is kind of like the characteristic thing of POM-DP planning. So one of the key things here is understanding the dynamics of the space and exploiting that for an efficient algorithm. So one of the key ideas that we came up with was that you can impose a partial ordering on the space, meaning that if, like, the geometric intuition is very simple. Basically, if you end up at the same physical state, the same low-dimensional state, with different covariances, if the ellipse from one covariance fits entirely inside of the other covariance, then it will always, like, if you follow the same path after that, it will always fit inside, it will always dominate, which means that you can discard the state with higher uncertainty, if that's all that you care about. And so that allowed us to develop this algorithm we called the RRBT. There's like a million RRT extensions, so we added the belief tree, rapidly exploring random belief tree. So this is kind of a 3D visualization of what that means. So the z-axis represents uncertainty, and you can see that we start at high uncertainty, and then the paths that traverse down to the green region drop in uncertainty, and then that makes it feasible to get up to the goal. So I realize I kind of like whizzed through a lot there. I don't know if anyone has any questions. Nope. All right. So this algorithm had nice theoretical properties. It was kind of an interesting area of the research where, like, clearly planning under uncertainty was a difficult problem, and there were a lot of different ways to approach it. It wasn't clear what the right one was. And this allowed us to kind of fuse reasoning about the dynamics with reasoning about the uncertainty. But when I got done with it, I was kind of left wondering, so what? Because it was an interesting line of research, but the more we pursued it, the more disconnected it seemed with the problem that we were actually trying to solve. And I think that this is kind of one of the tensions in robotics research, at least that I found, is that there can be this disconnect between the stuff that makes for interesting theoretical work and the stuff that actually makes, like, real robotic systems do what you want them to do. And this was, like, when we finished this was something that I spent a lot of time thinking about and ended up pretty frustrated with, because I felt like we had set down this path. Like, we had started by thinking about the theoretical aspects of the problem when we'd come up with this toy problem, and we played with it, and we'd done a good job of solving it, and we'd done something that was, like, interesting and got published, but it didn't really get us any closer to doing what we actually wanted to do. And I think from then on, I tried to kind of refocus the things that I worked on to make sure that they were, there's lots of different ways you can think about research, but for my personal taste, like, I tried to refocus towards things that were actually connected to the problems, and try to let, like, the data and the physics of the problem inform the kinds of solutions that we used. So the far other extreme of this was like, all right, we want to fly an airplane in some kind of aggressive way through obstacles. What should the airplane look like? So the first piece is you want it to be you want it to be able to fly slow enough to carry the sensing and computation payload. So that kind of suggests that you want something with a big wing. So maybe something like this. This is an RC glider. You also want it to be maneuverable. So maybe something like this RC aerobatic airplane. And then finally, to have a chance of being able to maneuver in these tight spaces, you need it to have a fairly small wingspan. So maybe something like this. This is called a Striker, which is a tiny little fast-flying RC plane. So it kind of pushed us into this weird corner of the design space where nobody was actually building a plane that did what we wanted it to do, because there's really no reason to do it unless you were trying to do what we were trying to do. So one of the constraints in play is you want to minimize the turning radius, and to do that, what you end up getting out is a fairly intuitive thing. You want as low a wing loading as possible. So this is an expression for the minimum turning radius of a plane. There's a couple of different things in play here. The big one is the coefficient of lift, CL max, and then the speed that you're flying. So it turns out the faster you fly, the tighter you can turn, but that doesn't necessarily work in our favor. But the thing that we actually have control over is the wing loading. And then a high coefficient of lift. Fly fast, not good for us. So in order to fly slow, we also want a high coefficient of lift. Not too surprising in a low wing loading. So one of the pieces in designing this was to select an airfoil. So there's kind of these are 3 different gradations of aggressive airfoils. So the more curvature, the more camber the airfoil has, the more lift that it'll generate at low speeds. So this is one of the trade-offs to be made. And these are the lift coefficient plots for each of those airfoils. So the penalty that you pay for having something that's very curved is you start to incur a high pitching moment, which means that the airfoil will tend to always want to pitch forward, which means that you have to do things outside of that in the design to compensate for it. And so it turns out that in order to do this, you're better off basically just making a really big wing rather than trying to squeeze as much as you can out of the airfoil. And within the wing space, we constrain ourselves to a 2-meter wingspan. So then the thing that you can sweep is the chord. And if you make that too big, you get more of the pitching moment and the thing becomes less efficient. So there's kind of a sweet spot there. So we ended up with something that looked like this. So it was basically as big of a wing as we could reasonably fit on there for a 2-meter wingspan to carry the payload. And then the last thing, which wasn't easily quantified, but we knew that this vehicle was going to crash a lot. And this kind of evolved actually over the course of building up the algorithms and testing the thing. So the 2 things we did, we put this nice sort of like cattle guard foam bumper on the front to protect the $5,000 sensor that sat right behind it. And then it was also all kind of rubber banded together. So we have rubber bands that are holding on the motor pods there. And we actually got to the point where, like, pretty much any crash, the rubber bands would break, the thing would kind of fly apart, and then you could just go strap it back together. So we built a bunch of different fuselages, but we only ever had one wing that survived the entire project. So that got us to the point where we could carry the sensing and computation payload and collect data sets. So this was me flying manually around a very small space and continually almost hitting that column, but not quite, and collecting the laser data that you see on the left. And you can see that the laser data, I'll play it again there, so you can see it, is pretty different from the kinds of things that we were using in the first videos. Like, as the laser hits the floor and the ceiling, you get these like quickly varying kind of nonsensical patterns, at least nonsensical if you're trying to think about them in the 2.5D sense. And so we clearly had to come up with a different kind of algorithm to process this data. So stated simply, the 3D state estimation problem is just trying to estimate the rigid body state. So the position and orientation of the vehicle along with the associated angular and linear velocity. So it's a 12D space. There's different ways that you can parameterize the orientation. So RPY doesn't work particularly well. I'm guessing some of you come across this in your research maybe. But from an estimation perspective, you have 12 degrees of freedom, so you can think of it as like a 12D state vector. And there's kind of this spectrum of techniques, from particle filtering being kind of the most general and the most powerful, but also the most computationally expensive, to something like Kalman filtering, where you use a compact Gaussian representation. It's very efficient, low-dimensional, but it's also very restrictive in terms of what you can represent. Are you guys familiar with these?
We'll be covering those, I think, in a few weeks.
Okay, cool. Just a preview of the whole class here. So particle filtering is natural for laser-based localization, where you have a high-dimensional nonlinear measurement. The Kalman filter, on the other hand, is dependent on linearization. So whatever the system happens to be, in order to use a Gaussian and in order to maintain a Gaussian state estimate, you have to linearize it. And in order to do that, you have to make very restrictive assumptions about the environment. So things like point features and lines are really the only things that you can use. On the other hand, a particle filter requires about 10,000 particles. So a particle filter, like the basic description of a particle filter is you're basically simulating the system a bunch of times, and you're keeping track of the likelihood of each of those simulations. And in order to do that and get coverage of the space that you're trying to estimate, the number of particles scales roughly exponentially in the dimension of the state space. So for 2D example problems, it works great. For like 9D, it's kind of questionable, especially if you want to run onboard the vehicle. So that 10,000 particle number in particular would mean that we could do a measurement step onboard the vehicle about once every 2 seconds. And if you think about flying 5 meters per second around obstacles, like that's probably not gonna work. So the key idea, driven by the data and thinking about the problem at hand, that we developed to make this possible was essentially leveraging the fact that the laser, even though we're trying to estimate this 12D state space, the laser only has information about a subset of it. The laser measurement, if you think about it, is only going to be impacted by the position and orientation. Like no matter how fast you're moving or how quickly you're rotating, with some assumptions there, you're not going to change the laser measurement that you get. And so you can exploit that to get a much more efficient update. So the basic idea is using something like a particle filter to do the measurement update step, and then propagating that back to a Kalman filter, which we're using for the process, the prediction step, because all the prediction stuff using the onboard IMU is fairly close to linear Gaussian. So this is some results we got from the algorithm that we developed. So there's kind of a lot going on here, but basically each of these lines is a different partitioning of the state space. Each of these lines is a different partitioning of the state space. The metric that we're looking at is what fraction of them diverged. So we want this to be low. We want it to be 0. That means the algorithm is actually working. And then each line is a different partitioning of the state space. So blue is just position, so 3D. I believe green is position and yaw. So 1 degree of freedom in orientation, and yaw is a particular choice that makes sense because if you think about it, like the laser is getting this kind of planar sweep, and so it's going to be affected by the yaw of the vehicle more than it will be by pitch and roll. Then red is full position and orientation, and cyan, is that cyan? I actually don't know what cyan is, but I think that's cyan. Is the full state space. And so basically, like the more dimension we try to estimate with particles, the more particles we need for the filter to actually work. And the difference between the full state space representation and just position is a couple of orders of magnitude in terms of the number of particles you need, which means you're basically a couple of order of magnitude faster. Oh, I should have just gone straight to the key. So now the caveat here is that we gave ourselves a map of the environment to localize against, but this is using that algorithm against the data that I showed to get a real-time 3D state estimate. So this was post-processed, but it was running like real-time computationally on the actual computer on the vehicle. And you can see the covariance ellipses around the vehicle represent the uncertainty. I'll play that again. So you can see, yeah. So if you watch the 3D ellipses around the center of the vehicle, you can see they sort of like expand and contract in different dimensions as the system picks up information on different axes. Yeah.
Do you ignore laser hits that hit the floor or the ceiling?
No, we don't. We use them actually because so we're not rendering it here so that you can see the kind of wall structure, but the map includes the floor and the ceiling. And so when you bank sideways like that, you lose lateral information, but you pick up vertical information. And
Sensor you're using for this?
this is a Skyio LIDAR.
This is a single plane LiDAR?
Single planar LiDAR, yeah. So the reason, like, ordinarily estimating a 3D state with a 2D LiDAR, especially when you're moving arbitrarily, would be difficult. But by using the filtering framework and aggregating information over time, you can essentially use it so that all that motion just continues to refine your estimate on different axes. Any other questions? So the next challenge, in order to make the system work, is what can we do about planning and control? So one of the more common ways of thinking about airplanes dynamics is this notion of a Dubin's model. That people familiar with? Is this Thursday maybe? It's a couple months, yeah. So the basic idea with the Dubin's model is that you have a system that can either go in straight lines or fixed radius arcs. So it's a fairly common model used to approximate cars and airplanes because it captures like the broad features of the dynamics. And it works pretty well if you want to do path planning, like flying up high in wide open spaces. The problem is that it gives you trajectories that are just fundamentally infeasible because the turning radius basically corresponds to bank angle. And so when you plan in this way, you're essentially assuming that the airplane can go from straight and level to bank instantaneously, which most planes can't, ours certainly couldn't. And so what happens is if you actually try to follow this, you get these effects where when you get to the junction, you have this unexpected deviation from the path, which is, again, not a big deal if you're in a wide open space, but if you're in a tight environment, it's a problem. And so basically what we came up with is a way of a priori offline using a polynomial offset. So we would start with a Dubin's curve, so lines and arcs, and then parameterize a 1D polynomial, which is a lateral offset. So over the course of that trajectory, you can lay it flat, but we have some, follow this trajectory plus or minus whatever our polynomial tells us, and then solve for the coefficients of those polynomials such that we can ensure arbitrary derivative continuity at the junctions. And then when you optimize with respect to minimizing the squared error, minimizing the squared control effort, deviation from the path, whatever, you get these rather intelligent things where the polynomials tend to anticipate and smooth out the dynamic difficulties such that you get these like nice, smooth, consistent paths. Yeah.
Do you use a polynomial like in the lateral offset of the plane of the circle?
Yeah, exactly. So this is 2D. So you could go up and down, but we were assuming like basically 2D motion. So not straight and level, but moving in the plane. Yeah. And so we put all this together, we got some pretty exciting results after a lot of tweaking and tuning. But this is a flight that we did through the parking garage underneath this data center. We're going to what motivated us to start the company. So, at the time we were just working on this because it was interesting stuff. They were fun problems to work on. We weren't thinking about applications at all. So I'm skipping a chapter here. After MIT, Abe and I went to Google, where we were co-founders of Project Wing, which was Google's drone delivery program. While we were at Google, Google obviously cared a lot about drones. They were interested in delivery. While we were at Google, being out here, it was clear that there's just a lot of things. There's a lot of really powerful applications that people are starting to think about and talk about using drones for. So on the left, this is probably 3 or 4 tons of steel and a crew of 3 or 4 people, and basically their entire job is moving around an image sensor that could weigh 2 grams or something. They just want to do it in a very precise, controlled way. In the middle, this is a guy who's risking his life climbing to great heights so that he can hold a mirror to look on the underside of this bridge cable to inspect it. So there's probably a better way of doing this. And one of the, it's really sad things about these kinds of jobs when you start to research it. A lot of them are so dangerous that you can't even get life insurance for them because people get hurt so often trying to do them. And then on the right, everything that happens inside of a delivery warehouse is very automated and efficient, but most of what happens outside is still very slow and expensive and manual. So this in particular is one of the things that Google was interested in doing. So each of these, I think, has the potential to really be revolutionized by autonomous flying cameras and eventually autonomous flying delivery devices. The problem, as we saw in the original video, is that with existing technology, like a lot of these concepts are easy to imagine, but they're very difficult to deliver on. And I think there's an enormous gap between what people want to do with drones and what they actually can do. So at MIT, we were using a sensor that cost $5,000, weighed a couple of pounds. But the big bet that we're making at Skydio is on essentially commodity hardware that's going into a phone. So we want to be able to do the same thing with sensors that are a couple of orders of magnitude cheaper and lighter. So the core bet really for us is by putting the right sensors together in the right way with breakthrough algorithms. So the primary technology is computer vision and motion planning. We can deliver a step change in what existing products are capable of and really open up the power of the systems to many more people in much more interesting ways. So I'll show, in the video here. So this is video taken from our first prototype, which we built, I think, 8 or 9 months ago. So in each of these, we're basically telling the drone to fly straight forward, and it's using a real-time 3D map of the environment to interpret that and do something that's actually possible without running into obstacles. See stuff a little late sometimes. We have to test it on ourselves, of course. That's how you know it's really working. So this is one of the control modes we have, we call Magic Wand, but basically you can use your phone to point at it and then point to where you want it to go, and using a combination of the sensors on the device and on the drone, you can just get it to go there. So it's a much more simple, intuitive interface than using joysticks. So this was sort of the first demo prototype that we built, which we used to sort of show what was possible and raise a round of funding. So we raised a $3 million seed round from Andreessen Horowitz and Excel late last year, which I know sounds like a lot of money, but it's not in startup land. But it was, so using that, I think the exciting thing for us getting started was really like what's possible with these devices. And from our research backgrounds, like we knew what the different technologies were within computer vision, what you would need to do to enable these things to be really smart and autonomous. And so armed with some money and like the foundation of the technology, I think really like the most exciting thing that I've gotten to be a part of my whole life has been getting to build and work with the team of people that we have now. So Frank Dellert, I don't know if people are familiar with, so he was a professor at Georgia Tech, who's one of the leading researchers in the world on basically SLAM, using least squares estimation. So we convinced him to drop everything and come and join us. So he's on sabbatical now as our chief scientist. We recruited a couple of the best engineers from our project at Google. And then really like looking at the specific technologies we needed to make the system work. So Pieter Henry, for example, was one of the first. He's a grad student from University of Washington. He was one of the first in the world to do dense 3D reconstruction using the Kinect. We worked with him a little bit at MIT, but we knew that was going to be one of the key pieces of the pipeline. Josh, we also knew from MIT, so he did his PhD on motion planning and control for aggressive flight. We have Gareth from UPenn. So we have pretty good coverage of all the best research universities in the world except for Berkeley. but hopefully we can change that. That's actually not true. So Abe, my co-founder, did his undergrad at Berkeley, but still we'd like more. And then we've also have the core of a really good hardware team. So Steve McClure, who led product design for basically the entire history of the iPad, recently joined as our VP of hardware. And Ben Thompson was at Tesla leading the design of the mechanical system for their autopilot hardware, is also joining us. Zach is actually somebody who I used to compete against in RC competitions. So he's stuck with it. He's now continues to be world class. I'm no longer, and he's probably saved 10 or 20 vehicles from crashing as our safety pilot as we test and develop. So since we raised the money, we haven't really said much about what the product is and what we're building. But I will say that we've had world class researchers working on it for 8 months now, and we have some pretty exciting stuff that I think is going to be the core of a pretty magical product. And a pretty magical, I think there's going to be a turning point in the industry over the next 5 years. The last 5 years were sort of about getting the hardware polished and in place enough, such that it was at least something appealing enough to take out of the box and use. But I think the future is in autonomy and in making the thing smart enough to fly itself so that you don't need to be an expert pilot to use it. So that's what we're working on. That's it. Yeah.
I saw from the picture when you were 9 years old that you liked planes, but is there any reason why you would prefer planes than the quadrotors?
Yeah, absolutely. So the multi-rotors are great because they're mechanically very simple. It's basically 4 moving parts to be able to do whatever you want to do. But from an efficiency standpoint, they're pretty terrible. And they're basically nice because they're fairly easy to control and they're simple to build. But I think that one of the things that's going to happen as people try to push the limits and want to be able to fly longer and faster and have better endurance is wings will start to reappear. The challenge, it's just hard from a number of different perspectives because as soon as you start adding wings, you have to do real aeronautic design. You can't just sort of slap 4 motors and propellers on. Basically anything with 4 propellers will fly, which is not the case with wings on it. And it also forces a number of more challenging controls and planning problems, some of which we were starting to look at MIT. So I think that wings will have a comeback as people hit the limits of what you can do with a multi-rotor. Yeah.
But could you the some tasks that the rotors do that you need this possibility of standing almost still and doing things very smooth? Do you think this is possible with wings?
Yeah, it definitely is. So yeah, I should have said. So I think what will happen is you'll start to get these hybrid vehicles where there's different ways you can do this. So at Google, we did what's called a tail sitter, where we had a wing with 4 motors on it, and it could hover vertically like that using basically quad rotor control, and then it could also tip over and fly forward. So you sort of got the best of both worlds. But the tail sitter also uncovers a lot of what's difficult about doing that. So in hover, it was sort of a quad rotor until you got hit by a gust of wind, and then it was some weird stalled out airplane that wanted to be flying forward but wanted to be hovering, and it was a difficult thing to control. So there's different sort of morphologies you can pick there, which are maybe better in some ways, but you always have to tackle these kind of difficult aeronautical design and control design trade-offs. But yeah, I think that the ability to stay stationary is clearly critical for a lot of applications. Any other question? Yeah.
So is Skydio focused on kind of hobbyist guns, or are you guys trying to go into commercial space, or what?
Yeah, so we haven't announced the product yet. I think that the reason why we started the company and what's exciting to us is making the power of the platform available to a lot of people. I think that there's, from a consumer standpoint now, it's basically it's an RC toy with a camera on it, right? But I think that if it's smart enough to fly itself, and you can start to give people a tool that they can give high-level commands to, there's a lot more things that you can open up on top of that. And ultimately, I think that there will be pretty good synergy between the consumer market and the commercial market, similar to the cell phone. People don't really talk about commercial cell phones and consumer cell phones. There's just kind of like a really good phone that you can do different things on top of. People have different theories on the drone space, but I think it's likely we'll converge to some kind of point like that. Yeah.
Through work with the Google Wing, I guess how does that work tie into the work that you're doing now with Skyio, if at all?
Not at all. Well, no. So Google was focused on delivery. I think that so they were interested in doing like delivery of physical goods to people, similar to just like what the Postal Service does now. And in fact, one of the interesting things is that and one of the motivations for starting the company was in doing that, we tried to skip a lot of the hard problems that we're now trying to solve. Like the paradigm that we came up with was flying high, hovering, and then lowering down the package so that you wouldn't have to actually like navigate the world. You could just like hover high, use GPS, lower the package down. And the people that are actually doing like real work with drones now, I think are doing a lot of things like that to make it work. Like, agriculture is one of the more popular applications because it involves flying in a wide open field where there's nothing to hit. And like urban, delivery of medicine in Africa is another one because you're operating in like wide open spaces. So if you look at what people are actually doing, people are kind of trying to work around the navigation problem. But if you just take it head on and solve it, I think that that's going to open up a lot of cool stuff. Yeah.
So it seems like now you're building your own hardware in addition to the software. Do you expect that to continue, or do you expect to just do like a middleware for different types of drones? Or?
So there's a significant hardware component to what we're doing. Like, there's really no way, I think, to decouple navigation from hardware. Like, we care about the cameras, we care about how they're positioned, we want them calibrated, we care about the computer that we're using, and unless you can design that whole kind of system together, it's hard to be successful. So when we announce the product, it will have, it's a tightly coupled hardware software thing.
Yeah, I think you're going to announce the product.
I'm not going to say. Yeah, sorry.
Okay.
Yeah.
From the last videos you were playing, we could see that the vehicle was like basically stopping when it sees an obstacle and flying backwards.
Yeah.
Like that's the main avoidance of obstacles you have, or is there a way like if you're telling it to go forward, it will like contour the obstacle?
Yeah. So that was the state of the system as of 8 months ago. But I agree with you that was that's not good. And so having it smoothly and optimally anticipate what's coming and figure out ways to get around it is important, and is something.
In the state of the art, it's possible to do that without a preloaded map, like
Yeah.
directly sensing the environment.
Yeah. Yeah.
Are you doing anything to adapt for like predicting moving objects like here on the
Yeah, it's a great question. So moving objects are much more complicated. A lot of, I don't know how many people work on computer vision stuff, but computer vision gets much easier when you assume the world is static. And so the perception side of things becomes more challenging when you have moving obstacles, and the planning side becomes more challenging too, because in order to avoid them, you need to predict what they're going to do. So it's something that we certainly think about, and I think eventually will be part of the product. But it's, for V1, I think it's hard to say. It's certainly, in the worst case, like if something's trying to attack it and you have to escape, that's pretty difficult. Yeah.
Is the current work looking at using OB cameras for sensing the environment without any type of depth sensing?
Yep. Yeah. So there, it's definitely like a technical bet, but from just an information perspective, like cameras have all the information about the world. Like this is how we process and understand things. So the challenge is like, can you extract the information you need from those images? And it's hard, but if you can do it, you end up in a very powerful spot because you have sensors that weigh almost nothing, are cheap as can be, and can give you all kinds of different information. And in addition to just 3D structure, you can start to get semantic information and other things. Yeah.
Are you guys like building and maintaining like a dense map on the quad?
Yeah, and you can look at the people that we've hired. So we've hired people who do dense mapping stuff, so that's part of the kind of pipeline.
So will the product be like, we'll be able to fly for long periods of time and still work?
Yeah, so there's different, so we care about a map for navigation purposes. I'm guessing you're sort of thinking about like memory constraints and computational. Yeah, so we care about a local navigation map. We don't care about building up like a centimeter level accurate global map of everything we've ever seen. And so the way we've designed the algorithms, we exploit that to make sure that we can stay efficient no matter how long you fly. Yeah.
How would you say, in your words, that your research, your PhD research, related to what you're doing now?
Yeah. So I think pretty closely. So first of all, I'm actually a PhD dropout. So I had just finished my master's and I was starting the PhD program. And I was excited. I had like just gone through the whole mental thing of like, do I want to do this? Yeah, I want to do it. I'm excited to do it. And then the opportunity to go to Google came up. And so I left to do that. So I'm still technically on leave, I think. But I think that it's really central to it. Like all the things that we learned and the way to think about these problems, like pretty, over the first 6 months of the company, I basically felt like I'd spent my whole life like building up all this knowledge, and it was essentially to like pour an opportunity to pour it all into a product. So it was like a fun, exciting thing to do, and it still is. Like it informs. Like I spend less time coding now, but it informs kind of like the high-level decisions that we make and who we hire and like what skill sets are going to be important and those kinds of things. So I think that like I think like looking back on it, just for me at least, studying things that I was interested in kind of a low-pressure environment where you could take as much time as you wanted to understand things and really dig into like the low-level aspects of a problem, like all that stuff has been crucial to what we're doing now.
Would you say that the work with how when you had the winged aircraft, you had issues with thinking, changing how you need to perceive things?
Mm-hmm.
Is that work in particular being translated to your current project, or is it mostly?
Yeah, so none of the, I would say like, it's not like we took any of the stuff that we did at MIT and just like used that algorithm straight up. It's like, I think of it more, and with all this stuff in general, robotics in general, I think of it more as you sort of build up a recipe book of like knowing what the different algorithmic components are and what they're good at and what they're not. And then I think like most good robotic systems come from being able to have a really rich recipe book and think at that level and then put together the right pieces to get the system to do what you want it to do. Yeah.
You briefly mentioned that you're not doing as much coding day to day. Being the CEO, can you say anything about that transition for you?
Yeah, it sucks. Yeah, so I think that I didn't really know what to expect, and I definitely I remember in undergrad, I expressly did not want to be a manager. I wanted to stay technical and keep doing technical things because that's what I really like doing. And so now I'm sort of in the explicit manager position, which is not that. But it is, at a company like ours, it's still super technical. If we're successful, it'll be because we figured out what the right pieces of technology were to put together in the right way with the right people to work on them to make a really compelling product. And so I think more so than I really would have expected, it's almost just, it's working at a slightly higher level of abstraction, but it's still a lot like software engineering. You're trying to figure out what the right pieces are to put together, who can work on what, how long things are going to take, what you can expect for V1, what's more of a V2 thing, and trying to line all that up is still a really fun technical challenge. And it's also, as an early stage startup, our job is basically to build a great product. The strategy is pretty simple once you decide what you're going to build. And so I'm still very involved in the day-to-day development priorities and those kinds of things. Yeah.
I don't know how much you can answer that kind of question, but in the world of rising temperature systems and whatever, there's many companies that are trying to build exactly the same.
Yeah.
How do you feel about who's gonna win the race for that, in the sense of what will be the features that you'll need, what kind of key you'll need, and
Yeah.
sort of things.
Yeah, so you're exactly, so I think my simple answer is that I think the people that will win will be the ones who build great things that people like using. Like, it's very simple, right? And I think that doing that is harder than most people think it is. And we see this a lot when, we talk to investors. I think one of the reasons why we were successful raising money is because investors had seen pitches from people who have sort of a business angle or some concept for something they want to do with the drone, but no idea how to actually do it. And when you see their demo, it doesn't work. And so I think the number of people going after it is kind of indicative of the size of the opportunity. But I think the ones that are successful will be the ones who actually figure out how to make stuff work and make something that is valuable and does something people want it to do, which you see this in a lot of other industries too, is a very high bar. It's really difficult to do that. Yeah.
So you still think that the barrier will be the technical aspects of it?
So I don't think I think there's a lot more to it than that. There's this sort of regulatory thing happening. There's obviously a lot of, in any startup or any business really, figuring out exactly what the right product feature set is and the user experience and having these things all fit together into a nice consistent way matters. But I think that similar to the early days of the internet, there were all these startups like Webvan and Pets.com. There were people trying to go after a lot of the sort of different business opportunities, but most of the successful internet companies were more sort of infrastructure oriented, the browser that you navigate with or the search engine that lets you find what you want to go after. And now in the internet, we're starting to see a lot of the sort of higher level things built on top of that. I suspect that drones will be kind of a similar thing where most of the early success stories will be people that just make the drone itself work and do better things. And then the sort of more higher level platform, very targeted application stuff will come later. Yeah.
What kind of skill sets do you think are most important for a
Yeah, it's a great question. So I think the most important things I think are, I guess there's kind of three maybe. There's physical intuition for problems, being able to think about what are the physics of what's happening here, what are the kinds of decisions that the robot's trying to make, and how does that relate to the world around it. I think being able to formulate and think about those things mathematically is very powerful. And then I think one that's kind of underrated in robotics research is just software engineering skill. And this is something that we learned a lot about at Google. When we were at MIT, we were just writing slapdash research code in a repo that only we were contributing to. And being at Google and contributing to a large-scale software project and seeing what happens when you have 30 engineers working on the same kinds of thing and what kind of practices you can put in place, that stuff makes a huge difference. And I think if I had to go back and focus on something more, it would probably be just the software engineering, because any kind of robotics thing, there's all kinds of interesting algorithmic challenges and sort of researchy things that go into it, but at the end of the day, it's mostly a giant software project. And things like software testing and simulation make a huge difference in being successful or not successful at this kind of stuff. And especially, I think that was a particular thing for me because my undergrad was mechanical engineering. And so I didn't have the undergrad foundation in computer science. I had to consciously decide to pick it up and learn it. Yeah.
Some people in the room might want to know your status for hiring interns or hiring intern capacities.
Yeah, so that's part of why I'm here. So we're definitely in a hiring. We're hiring good robotics engineers. So if you're interested in computer vision, perception, motion planning, any of these kinds of things, definitely reach out. I have my email here. I'd love to hear from you. And we also have a website where you can submit an application, or we can just chat afterwards. That's probably even better. As far as internships, so we haven't. I'm guessing this would be for next summer. So we don't actually have an official intern program. I suspect something like that will come online over the next year probably. But I guess what I would say is if you're if you're looking for an internship and something I've said like resonates with you and you're excited, definitely reach out or come chat. Anything else? I think we run 15 minutes over.
No, I mean, we have the room until 5:30, so we, in theory, could go another 18 minutes.
All right.
But it seems like there's not many questions left.
Yeah. Anything else?
Any closing thoughts?
Will you do actual object recognition in the next step?
Object recognition?
Yeah, like actually recognizing people first in order to model more object groups.
Yeah. Yeah, that's one of the reasons why we decided to use vision, is because it opens up those kinds of possibilities and you can start to use that information to make the whole system perform better. So this is one of the themes that I didn't touch on as much, and this is maybe a dangerous thing to say in an academic setting, but I kind of believe that the most interesting work in robotics, I believe, over the next 5 years is going to transition from happening in academia to happening in industry, because all the sort of supporting technologies have bubbled up to the point where it's possible to make real systems work. Like up until now, the Roomba is like the most successful commercial robot ever, and it's pathetic. Like somebody from iRobot will see that. I don't know if they dispute that. Like it's basically like bumps into things, and it's so far below like what we know how to do now. And I really believe, and I think we see this every day in the system that we're building as it comes to life, that the supporting technologies are all there, and there are multi-billion-dollar markets that you can build things to go into. And I think similar to like, if you wanted to do distributed systems research, you wouldn't go into academia, you'd go work at like Google or Dropbox or something like that, because the scale of what they're doing and the data they have available, and the fact that, Google will pump billions of dollars of R&D into that kind of stuff, makes it just like a much more exciting, higher leverage place to do it. I believe that the same thing is going to happen with robots as well. So that was a long-winded question to object recognition, but I think it's one of the things, like it's hard for academia to build really complex software systems where you have all these different components that interact in a powerful, unified way. But it's something that, it basically is what companies do, because you have the scale and the data to do it. So using an object recognition system alongside of a SLAM system to make both better is difficult if you don't have either of those. But if you have a team of people working on each, it's easy to it's easier to integrate them together into like a cohesive, useful unit. All right.
I have a question related to that question. In industry, you guys do a lot of sort of systems integration type things. How often do you pull from research that was done in academia?
All the time.
All the time, okay.
Yeah, all the time. Like I think that's one of the bets for us, is that this stuff, the research that's, robotics research has been going on for a long, long time. And I think over the last, since the probabilistic robotics movement or whatever in the late 90s, like I think that stuff has really come to fruition and is ready to be harvested and turned into products. So we do, we pull from academic research all the time, and we don't publish this stuff, but I think that what we've built on top of that, we probably have, a bunch of conference papers if we wanted to. Like we're constantly pushing the state of the art in what we do, but we're doing so just very focused, directed towards a product.
Thanks.
Yeah.
Any other questions? Okay, well, thanks Adam again.
Yeah, thank you for having me. It was great.